This is part 4 of a series on geometrically interpreting the chain rule in multivariable calculus. My name is Bill Kinney. In the last part, we finally got to the geometric interpretation in the context of thinking about the derivative of this function, ultimately based on a change of coordinates to polar coordinates. We are composing that function with this function where that capital phi function is given by this formula. This is a formula that transforms a point in polar coordinates, or in a polar plane, you might say an r theta plane, to the corresponding rectangular coordinates. When you visualize this, when you think about this, normally we think about it in terms of the plane on the right, the ordinary xy plane, and we imagine that given a point in that plane, focus on the point on the right here, that we have some rectangular coordinates for that point. For example, it looks like this point has perhaps got rectangular coordinates of about 0.9, 0.9 or so. And we could transfer that to polar coordinates. We can use the equations, actually r equals square root of x squared plus y squared, and the fact that tangent of theta is y over x to figure out what the polar coordinates would be. And if we did that, we would get, looking over here, we would get r to be about 1.25 or so, and theta to be about 0.75 radians here, it looks like. But we normally don't think of this plane on the left. This is something new. We're thinking about a new plane on the left here, an r theta plane, and we're imagining the capital phi function as transforming this point at the point 1.25, 0.75 to the corresponding point at about 0.9, 0.9 in the xy plane. All right, and so we were focused on the chain rule for the particular function f of xy equals x squared minus y squared based on this polar change of coordinates. I'm going to copy and paste the main results down here so we can look at them. Get rid of some things here. I'll get rid of that. Here are our main final answers, you might say. And what I want to do in this video is I want to focus on how to interpret these things. Before I do that, though, I think I should review very quickly an important thing about derivatives that I hope you remember from Calculus 1. If you got y equals f of x and you differentiate that and get a derivative, you can approximate the change in the y value by taking the derivative at a given point x. I could write that as f prime of x, but I'm sticking with Leibniz notation here, so I'm going to write that as dy dx, but it is evaluated at a particular value of x, and you multiply that times the change in x. If you multiply by the derivative, the rate of change, by the change in x, that's going to give you an approximation for the change in y. This is a fundamental approximate equation in calculus, perhaps the most fundamental approximation in calculus. To find the change in y, you can approximate it by taking the derivative of y with respect to x at whatever x is and multiplying by the change in x if you allow x to change. All right? We're going to think about that here in this context. I'm at this given point. What happens if I allow r to change, and what happens if I allow theta to change? Well, the derivative is going to tell me how much I should expect z to change. If I change r a little bit, I would plug in the value of r and theta at the given point into that formula to get the derivative, the rate of change of z with respect to r at that point. And then if I change r a little bit, I would multiply this number by the change in r. Same kind of thing if I change theta a little bit. I'd use this formula, plugging in the point that I'm starting at, in this case the polar coordinates of that point, r comma theta, into this, get a number, and multiply that number by the change in theta to approximate the change in z. So for example, if I'm at this point and now I imagine changing r a little bit, I'm actually going to do that up here. This slider will increase r a little bit. Watch on the right, well, both sides. That little blue line here extending from the point horizontally down here and in the radial direction away from the origin over here represents a little change in r. you can see based on the level curves in either picture actually that the function output isn't changing much. This blue line is practically parallel to this line along y equals x here. It's practically parallel to this line at theta equals, actually that would be pi over 4 right here. And the value of the function is not changing much. That derivative, that rate of change, would be very close to 0. Maybe slightly positive because we're going slightly to the right here toward the lighter values, the higher values. But it's not much of an effect. That derivative would be very small and the change in z would be very small. Let's just pretend, for the sake of argument, that the derivative there is positive 0.1. I would take that positive 0.1 and multiply by the change in r here, which looks like it's about 0.2, 0.3 or so. 0.1 times 0.3 would be 0.03. Maybe you want to write that down. And that would be your approximate change in z. Again, if this derivative is 0.1 and I increase r by about 0.3, then the approximate change in z would be 0.1 times 0.3, approximately 0.03. How about if I change theta a little bit? In the plane on the left, we're going straight up from the point. In the plane on the right, you can see we're not going straight, we're curving. R is staying constant and theta is changing. So that's got to be a curve if theta is going to stay, if R is going to stay constant. However, when the change in theta is small, that green on the right there is close to being a straight line. You can effectively, derivatives measure instantaneous rates of change. This approximation idea is only good for very small changes in the variable. What would it be here? You can notice as theta is increasing, we're going toward a darker region. The derivative with respect to theta is going to be negative here at this point, and the change in z will therefore be negative. If I increase theta by, say, about 0.3, maybe to about there or so, and if I pretend that this rate of change, the derivative down here, I'd have to actually plug in numbers to figure it out. If I pretend that derivative is negative 0.3, then the change in z would be negative 0.3 times 0.3, approximately, which would be negative 0.09. So you could expect the function value to go down by negative 0.09. What are these arrows over here? These are vectors. These are special vectors. This red one here is the gradient vector. The blue one is a unit vector, a vector of length 1, pointing directly away from the origin. It doesn't matter what point I'm at. And again, the red one is a gradient vector. And what's the green one? The green one is actually this vector here. In fact, all these vectors are in these formulas. The gradient of f is the red one. This vector right there is the blue vector. That's a unit vector, always length 1, no matter where you are. And this vector right there, that's the green one. It is always orthogonal to the blue one, or perpendicular to it. Although this picture, it looks a little deceiving. It looks like it might not be exactly perpendicular, but it's supposed to be. I'm not sure if the scale is off a little bit. But that should always be perpendicular to the blue one. Anyway, I'll wrap this video up by just noting that the derivative with respect to r can be thought of as the gradient of f, the red vector, dotted with the blue vector. You can see that, for example, when I'm over here, that dot product is going to be negative because the angle between the red and the blue is negative. And indeed, if you change r a little bit, go in the radial direction, you can see the function value is going down. Okay, so this angle is going to be, if it's bigger than pi over 2 radians and less than pi radians, then you are going to get a negative rate of change here. And this dot product is the angle related to the angle between the red and the green. That's an acute angle less than pi over 2 radians. So that dot product is going to be positive. This rate of change is going to be positive. And yes, if you move in the angular direction for a constant r here a little bit, you can see the function values are going up, going from dark to light. I'll let you think about that. I might make another video, I might not, I'm not sure, but you should certainly stop and think about that. If I do make another video, I'll probably try talking about the same stuff with particular numbers.